So why do we need it? That's the question. Okay. So let me start with advertisement here. So electron beam direct writer is coming to campus finally. So it is Raith EBPG plus electron beam writer is coming to our clean room sometime this year. So this system is ultra high performance electron beam lithography system with a 100 kb electron energy. And because of the high electron energy column together with all the advanced design, we can achieve resolution below 5 nanometers, which is quite impressive. Well, of course, it depends on what do you want to do after you do writing. So post-processing has a significant influence in the resolution of the final features you're trying to do. But when it comes down to, when we are talking about E-beam writer only, this system is quite good. It's truly the best, well, one of the best systems on the market currently available. And together with EBPG Genesis Beamer software, which is the most comprehensive lithography software to optimize many things. So the software is coming together with the EBPG, electron beam direct writer system. We are going to have a workshop for EBL on June 18th. And according to my understanding, we are going to have a talks by 2 vendors. And the registration site will be ready soon. Do you know anything about registration? I'm not involved in that part, but soon it should be ready. That's my understanding. Okay, so this is what we are going to talk today. Nano-fabrication in general, and can photon-based lithography do it all or not? And electron beam lithography, why do we need it? Followed by electron beam resist and electron beam lithography processes. And talk about the hardware, EBPG plus, and at the end, I hope I have some time to cover this one, the proximity effect and correction. That's a big thing in the EBL field. Nano-fabrication. So in the clean room, our clean room, we have a contact printer, optical lithography system, or mask aligner. Those are the names, meaning the same thing. We can make features down to about a micron, 1 micron-ish, if you do everything correctly. So photon-based lithography in our lab clean room, maybe going to here, about a micron. In practice, easy to do 10 microns, 100 microns, no issue, but going down to making 1 micron by 1 micron square with a contact printer optical lithography system is a little bit challenging. So E-beam lithography coming in to cover this range, 10 down to smaller, and now we can go down to 5-ish here. By the way, the photon-based lithography, we can go down to 10 nanometers nowadays, maybe smaller than that. But it's very different photon-based lithography is very different from EBM, electron beam direct writing system. Okay, we have to talk about photons first. MOSFET scaling, metal oxide semiconductor field effect transistors, which we have so many of them in our computer, cell phones, and everywhere. So the integrated circuits are based on field effect transistors. It started in 1960s, and at the beginning, we have a 10 micrometer technology here. And I checked my office computer, Inspiron 3880 desktop computer. It has a Core i7 10700. That's the Intel chip. And that uses 14 nanometer technology. So it's here. How much do I pay for this computer? Maybe 500 to 1,000 together with everything, but we already have 14 nanometer process node technology here. Okay. And it has 3 billion CMOS complementary MOSFET transistors, MOSFET here. Okay. So optical lithography is photon-based technique. And the strongest advantage is indirect writing. So it requires a mask, but exposure is so short. So you expose and you have, for example, if you have a 12-inch silicon wafer, it can produce approximately 400 dies, so 400 CPUs in one wafer, okay, with a 14 nanometer technology. So it's very quick. For industrial process, speed is so important. Okay, so optical lithography's resolution is mostly determined by wavelength of the light you use. So typical optical lithography contact printer mask aligner thing, we use mercury lamp. So shortest of mercury line, which is I line, is 365 nanometers. It's UV, but still huge. It has still huge wavelength there. And to make things smaller, 365 nanometer is way too long. So you have to start going down in the UV. So deep UV, 248, 193, 157, 126. And EUV, extreme UV, is between 10 to 121 nanometers. So if we can use 13.5 nanometer source, yes, we can make very small devices. Let's check the Intel's roadmap. So we are 2024, Q1, Q2. So Intel 3, that's the process. And we are in the extreme UV technology, that's exposure technology. So this one, yes, they are making 2022. So it's less than 5 nanometers. That's process node. So Intel can make very small thing using photon-based technology, extreme UV technology here. What kind of instrument tool do they use for photon-based technology for EUV? EUV is, it's waste, basically this is the system, contact. So that this is the EUV exposure system, weighs 180 tons, costs more than 120 million. And in 22, this company, I think ASML, sold 258 photolithography systems. So big one like this, all automated. And out of 258, only 31 are EUVs, extreme UVs. So for us, or for any academic clean rooms, EUV is too expensive. That's one thing. And the other thing is not flexible. Okay. So if you have a mask and trying to make so many of same devices, it's fine. Flexibility is not important for Intel. But for academic environment, we don't need tens of the dies. We just want to have a few working devices to prove the, the concept of the device for the most of the time. And if you have ever seen the optical lithography masks, it's very simple. Okay, so you have a glass, soda lime, or a quartz substrate, and you have a chromium pattern or something like that. It's very simple. While EUV masks are very complicated. So it's not like substrate with single layer patterns on the top. So it has so many layers, so making this mask, preparing this mask is very difficult. And I think it's they have to use EBL technology to prepare EUV masks. You have to have an EBL capability to use the EUV systems. So why we need it? Because we cannot use EUV technology in academic clean rooms, I think. It's too expensive. And after looking at 120 million ASML EUV system, up to 5 million electron beam direct writer price looks reasonable. It's still expensive, but it's much better than 120 million. And E-beam writer, direct writer is a better tool for this research environment because of the flexibility. Direct writer, so that means we don't have to have a mask. And for most of the time, speed of writing is not super important for academic clean rooms. Okay, not like as in the production environment. We are not Intel. So typically, we use mask aligner for microstructures. To make microstructures, we use the mask aligner. This is MJB4 from SUS Microtech. And for nanostructures, electron beam direct writer works very well. However, when it comes, when we are thinking about technology, the physics, we need to have EBL here for nanostructures, and the equivalent in the micro scale is the mask writer. Heidelberg mask writer. It uses optical beam, and this is direct writing system. Okay, so no mask, and actually the Heidelberg mask writer is mostly used for making masks. So we use contact printer for micro fabrication, but the technology, this is the indirect writing system. So we need a mask for mask aligner, while EBL, the electron beam direct writer, does not require masks. Okay, electron beam lithography is used for two major purposes: very high resolution lithography and fabrication of masks. I don't think we will get the user who needs to have a mask in our facility. But yes, it's capable of doing such a job.
Because you would typically make masks using some other tool, Tomoko?
So we don't have EUV system or
Right.
deep UV system. So
Yep.
yes, in theory, we can use, the electron beam direct writer to prepare mask, but no one can use it in a clean room. So
Right.
Intel, I think they have an E-beam writer and they are making masks for EUV systems, but not for us. Okay. And EBL is popular in research environment. It's flexible. We can change design anytime. But if you have a contact printer, the mask aligner, when you want to change the design of the device, you have to start working on the CAD file and, bring it to the mask writer and develop and prepare everything. So it's not that easy to make small changes for indirect writer, contact printer. But for EBL, the E-beam writer is so flexible. So you just need to change the design in the CAD file. And in this sense, it's a fabrication of non-conventional devices, such as qubit. And, whenever you have to change the design so many times, it's so convenient. Okay, electrons. Why so much better in resolution compared with the photons? Okay, so wavelengths EUV is about 13.5 nanometers, so it is here. 100 kb electrons, equivalent wavelength is much shorter, okay? Electrons can achieve much better resolution because of, how do I say, being electrons. They are not photons. Of course, EBL has advantages and some disadvantages. EBM allows fine control of nanostructures. So typically, these numbers are typical numbers, lateral resolution of 10 nanometers or better, placement accuracy of 1 nanometers, pattern in field of 1 millimeters. This is for E-beam writer dedicated system. Flexible direct light, no mask, wonderful. No diffraction issue. So optical lithography often hit the diffraction limit, so we cannot make something too small. Wavelength related. The major disadvantage of EBL is slow. It's the serial writing, no mask, but you have to expose, not quite one by one, but yes, you have to. Beam needs to move around to expose. It's very different from mask alignment concept. And we have to deal with proximity effect. I hope I have time to cover it at the end there. Pattern transfer is required. Yes. And often pattern transfer process limits its resolution. Well, this is not the disadvantage of EBL. Any lithography system involves pattern transfer process afterwards, pretty much all. So we have always need to deal with the pattern transfer, and you may lose resolution during the post-processing time. Electron beam resist and electron beam lithography processes. Yep. This is how it works with the positive resist. Start, you have a substrate and a thin coating of E-beam resist. Thickness depends on what you are trying to make and what you are trying to do as a post-processing step. And you have to prepare a CAD file. So you put this information to the computer and electron beam expose. Okay, this is the positive resist process. So expose outline here. Okay, so after exposure, what happens with the positive resist? Well, PMMA, electron beam energy will be used to break down backbone of polymer PMMA. So it's making smaller segments after exposure. So those smaller segments can be washed away during the development step. Okay. So after development, we have exposed area removed. Okay. Positive resist system process, exposed area will be gone. Negative resist process, exposed area will stay. Those are differences. So this, I did not do this lithography, but I found it, so somebody did it. And even though this is the SEM converted, and the SEM is the not even the field emission system, is a tungsten filament system, and maybe 30 kV or something. It's very primitive E-beam writer, but you can still do 50 nanometer lines. Electron, thanks to electrons. Okay, EBL process, more like general cover. So you have to do many things. Here, you have to plan what you want to make and think about all the processes, and you have to do CAD design. Then you have to convert the pattern to something the computer can, E-beam writer can read. And wafer preparation, mostly cleaning, pre-bake or whatever, then put the resist and heat it to remove excess solvent, get ready. And if the solvent, so the substrate is not conductive, you have to put some conductive layer on the top. And of course, if you want to align to the already existing system, you have to prepare this part. And expose. After exposure, development, post-processing, etching or lift off typically, and go to the next step. E-beam writers, they do only this part. Well, little bit of pattern conversion, but only this part. Okay. So complete overall EBL process is much larger and more involved than just using E-beam writer. Okay, let's talk about electron beam resist. Very famous ones. PMMA, tone is positive, resolution pretty good, but sensitivity is so high. Oops, this is supposed to be microcoulomb per square centimeters. I should update this one. I was supposed to do that, but I forgot. PMMA, historically famous, but still many people do use it because of the resolution. However, sensitivity is high. That means you have to put a lot of those. Developer is simple, MIBK plus IPA, so it's good. Z550, also a positive resist. Resolution is not as good as PMMA, but sensitivity is better. The developer is solvent. HSQ, I would say the most famous negative tone electron beam resist. Resolution good, sensitivity not so great. Developer is the aqueous alkaline solution. For optical beam optical lithography, we use both positive resist and negative resist, and the choice depends on what kind of pattern you want to make. But for EBL world, the major resists are positive ones. only special occasions we wanna use negative resist. Okay, E-beam post-processing with a lift-off. So you start with a, sorry, this is the double layer recipe. So you have a substrate and you have first layer resist. And top is the high resolution slow resist, PMMA. Both are positive resist. So that means exposed area will be gone after the development step. Okay, 950K PMMA. PPMA. That's it. Okay, those positive resist average molecular weight defines resolution. So you want to pay attention what kind of average molecular weight PMMA you are using. Okay, 950K or 1 million-ish is very good in terms of resolution. Line width would be very small, but it requires more dosage. COP, copolymer, co-methyl methacrylate, co-methyl acrylic acid. This is much faster resist. So when you are exposing to E-beam, COP will be exposed more. So it creates undercut shape, which is ideal for lift-off process. And after you deposit metal and the strip of the resist, you have a thin line left on the resist. This is the lift-off process. Instead of lift-off, we can do the etching as a post-processing. So yes, you can do PMMA as an etch mask, you can use it. However, PMMA etch rate with this is the fluorine-based dry etch CCP, so coupled, so regular RIE system, etch rate, it's quite fast for PMMA. So often people wanna use the Z550. So it's slightly better etch rate. Okay. This is simpler than lift-off. So you have a substrate, E-beam resist, exposed E-beam, and after development, exposed area will be gone because it's the positive tone resist. And you do perform dry etch. And after dry etch, you can remove whatever the leftover resist. Then you have a trench on the substrate. If you want to make this kind of structure, you can use the dry etch as the post-processing. Okay, negative resist, HSQ. I can pronounce hydrogen, but I cannot pronounce the word start with S after hydrogen. Okay, HSQ is the most famous negative resist. And historically, it's supplied by Dow Corning. Many people use it, but it has terrible shelf life. So only lasts 6 months at -5 degrees C. And the lead time is crazy and uncertain future availability and super expensive, much more expensive than PMMA or ZEP. ZEP, I don't know the current price, but HSQ is quite expensive. So when I purchased 100 milliliters or 200 milliliters of resist 10 years ago or more, it was like $1,000 for that one. And that can last only 6 months. As a resist, this is truly expensive one. But it has advantage. Okay. So you have something, substrate, and you have something. And you put the negative resist. E-beam exposure, this is negative tone resist, so exposed area will go under cross-linking most likely. And after development, unexposed area will be gone. So you have something like that. Then you put it in the dry etcher most likely. And after etching and remove everything, cleaning. So you have something thin line pattern on substrate. It's useful when you want to make waveguide structures. Okay. So when you want to make photonic crystals or coupled with waveguide structures, the HSQ negative resist process is very useful. Okay, let's talk about E-beam writer we are getting. Website is here. And speaker from the vendor will be coming, the remote talk, but if you have any questions about specific about this tool, you should prepare and ask that person in our June workshop. 100 kb columns. Yay. Great. 100 kb thermal field emission electron column. Yes, we need to have field emission for better, smaller beam size. And also 100 kb, higher the kb. Generally speaking, you can make spot size smaller. That's good. However, the important part of the hardware of E-beam direct writer is not too much about 100 kb. Well, it's important, still important, but column needs to be stable. Okay. For E-beam writing process, shorter one goes like maybe 10 minutes, 1 hour. Sometimes you have to, you need several hours or overnight writing. So stability of column, beam stability is super important. We don't want to change it. This is not a requirement for SEM imaging or TM imaging. Well, if you want to do tomography, it's maybe a difference. So let me talk about SEM. SEM imaging. To take a nice quality picture, we don't need very long time, not 1 hour. So column stability is not super important for SEM as a characterization tool, but E-beam writer as a fabrication tool, that is super important. And also, not only the electron beam itself, but you have to have a fast beam blanker and other hardware requirements specific to E-beam writer. That's important. And you combine all the advanced hardware technology in addition to 100 kb thermal field emission electron column, we can achieve sub 5 nanometer pattern. Okay? The system we are getting, the max current is 350 nanoamp. That's huge. When we use tungsten filament-based SEM for EBL, I use 5 to 10 picoamps for high resolution lighting. So if you want to draw 50 nanometer line using the tungsten filament SEM, we have to use 10 picoamp or lower for that system. But for the E-beam direct writer, we can use much higher beam when the resolution is not important, and it can change the beam current during the writing. You can specify the beam current. So for high resolution, you can use the different beam size. And when the resolution is not that important, you can increase the beam size. So it's very flexible, automated.
Will you be able to observe the pattern under this tool that you create?
Which one?
The
E-beam writer. Maybe, but it's not designed that way. So it's not the SEM. So yes, it can do something similar, but two things. Number one is you perform E-beam writing and bring it back the resist pattern to E-beam writer, or it's same SEM to check it. Then you are adding the additional doors to the resist pattern. You may ruin the pattern. Okay. So do we want to do it? Maybe not. Okay. So after you transfer the pattern by etching the lift-off, yes, we can do that. But do you want to bring it back to the E-beam writer to characterize it? I wouldn't do that. SEM is much easier.
Right.
Or if you want to, you need to characterize the E-beam resist pattern, I would use AFM. It's much, it's tedious. You have to find a particular area. It has its own issues, but it does not damage. It does not change while we are looking at. So AFM was the one I used a lot to check my resist pattern. Once it's transferred, I can put it in SEM. No issue. Okay. Field emission, why it's important? Okay. So this is the typical figure from SEM or electron beam, electron microscope book. Okay. Field emission. Schottky is thermal field emission. So this E-beam writer uses this technology, this field emission. This one is the cold field emission. So when the current is relatively small, the probe diameter, beam diameter does not change too much. So up to around here is reasonably high current with a reasonably small beam size. That's a good combination. While thermomic emission, tungsten filament or RAP6, it's kind of going that way. So as you increase the probe current, probe diameter increase too much. So this is the reason why I could not use 1 nanoamp for 15 nanometer line lighting. Okay. So the beam size, well, 100 kV, higher, important. Okay. So 30 kV, that's typical SEM energy. Not bad, it's still small relative to photons, the mercury lamp in particular, but higher the better in terms of resolution. But resolution is not the only important thing in the EBL. Okay, let me talk about comparison between the SEM converted EBL system versus dedicated electron beam writer. It's not about resolution. Resolution, 5 to 10 nanometers. Maybe it's with a modern E-beam writer, less than 5 nanometers. But about the same. Secular rating voltage. SEM is typically designed 30 kV or lower, while the dedicated system is 100 kV or sometimes 50 kV. Deflection bandwidth, that's how fast beam can move. Kilohertz versus megahertz, much faster. The field size is variable for SEM converted one. Dedicated system is about a millimeter-ish. Field stitching accuracy. It's very difficult to get good stitching accuracy with the SEM converted system. While dedicated system, we can do 10 nanometers or better. Beam error feedback, that's special features for dedicated system. Stability of the column, good for dedicated system. SEM conversion. So SEM is not designed for stability. So it's not important here. Magnification for, I think it's most likely fixed for E-beam light. So, and we don't have a lot of flexibility when it comes to magnification and field size and those things with the E-beam lighter. So that's why it's very difficult to use it as an SEM. Okay, dedicated system. Let me do it short. Speed, fast, accuracy, more accurate, automation. Thank you. Well, you have to do so much. You have to pay attention so many things if you have to use the SEM converted EBL system. So its automation is really important part. EBPG will be most likely exclusively operated at 100 kV energy. I don't know if we can switch between 50 and 100, but I don't see the reason why to operate at lower kV if the system is capable of using 100 kV. To change the spot, you choose the different aperture. And when I want to make 20 nanometer wide lines, the spot size should be smaller than this, definitely. So it's about 5 nanometer would be nice, so you can choose which combination use. And you can change different current, different apertures, and system will switch automatically. That's beautiful. You cannot do that with a SEM. So recap, 100 kV overlay, so it's better than 5 nanometers, stitching better than 8 nanometers, maximum beam current 350 nanoamps. I don't know how often we want to use large beam current, but it's available. 20-bit field digital analog converter, 14-bit subfield DSC, 15 millihertz, megahertz exposure clock. And you can make various structures here. By the way, so this one, I believe this is a 5 nanometer lines. Okay, proximity effect. Blah, 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 blah. So this is the pattern. And if you do not make any corrections, so let me go to the other one, sorry. So this is the pattern. And if we use single exposure, so everything is in green color, this is the result after development. Okay, so typically the incident electron beam size can be very small, 2 nanometer or smaller or whatever, by adjusting current and the energy of electron beam. And the forward scattered electrons, the beam size stays small, okay? Great. However, backscattered electrons, the beam size is huge, depending on substrate material and also kV. So the dots in the center, it can feel all the contribution from neighboring exposures. That's, in short, proximity effect. Okay, so the center, if your pattern is isolated square here and next square is far away, you don't have to worry about proximity effect. However, if you have set of squares, the center square receives more dose than the square near the edge. Okay? So that's what happens here. So you have to adjust the dose depending on the geometry of your design. So you have to do the proximity effect correction. Then after correction, so it's each dot receives slightly different dosage, and you can get the pattern you want. So without correction, it's going to be like this, and photonic crystal may not work as you intended, while this pattern with a correction, that's great. So proximity effect correction is one of the many things Genesis Beamer software can do. I think it's that Raith has the software package like that, and I don't know which one does the proximity effect correction for us available, but software component is important to get a good result. Okay, so I was not involved in the purchasing process of e-beam writer, so I don't know the proximity effect correction is coming from different package from the e-beam writer vendor or software, the Genesis Beamer, but one of them will take care of it. And Beamer, in addition to proximity effect correction, it can do many things, and we can do much faster writing. The writing scheme would be optimized. Okay, so let me go back to this slide.
So Tomoko, just to interrupt you.
Yes.
Yeah,
Yes.
the proximity is coming from Genesis.
Oh, okay,
That's
from
the
Genesis. Okay, not
Genesis,
from Raith.
and
Okay.
yeah, but it's part of the package from Raith. They work together. They actually collaborate together to put that on their system. So yeah.
Yeah, because Raith has their own proximity correction software package, right?
Yeah, they have, but it's not as powerful as the.
Oh, okay. So Genesis Beamer is a better software. Okay, I see.
Yeah, correct.
Okay. So I'm almost done, but I want to go back to this slide. Exposure, that's what e-beam writer can do. But EBL process involves many other steps. Okay. So e-beam writer won't be available tomorrow, but you can start preparation now. Okay. So many steps you need to optimize to have a, before even expose it, before you put the wafer into the e-beam writer. So you should start preparing now than later. Okay, it won't happen in a week. Okay, so you have to prepare everything in advance. So it's a good time to start, or you want to start thinking, planning, and you may want to get ready and ask all the questions during the workshop to the vendors.